Good afternoon. Welcome to this afternoon's Brew and View, sponsored by MasterCam. My name is Dave O'Neill. I'm the Vice President of the Media Group at SME. So this afternoon's presentation from Stas Mylek is on dirty little secrets about cutting tool performance. It'll be about a 40-minute presentation, so go ahead and get something to eat. There's beer in the back, get a drink, and then we'll do probably a 5 to 10-minute Q&A at the end. So with that, I'll turn it over to Stas, and then we'll get rolling. Thank you.
Okay, thanks. All right, I'd like to thank SME for the opportunity to present today. Hopefully you guys got an opportunity to grab some beer and some food. Hopefully this presentation is gonna, we're gonna have a little fun during this session. And we're gonna talk a little bit about the dirty little secrets of tool cost. And let's see if we can get started here. Okay, so I'm gonna start out with a question. Do you really know what's lurking behind tool price? Now, I'm going to use two terms here. One's price, one's cost, and there is a difference. Okay? When you talk about tool price, it's really the cost of the tool. If you were to look at a catalog, that's your price. But in essence, what we're going to try and get down to is the actual true tool cost and how you can use that to gain additional profitability in your jobs. Okay? So, we're also going to expose some myths and some preconceptions that you might have. We've talked to a lot of customers, a lot of people out in the field, and there are some interesting notions out there. And hopefully we're going to challenge some of the common practices that you might see out there or even experience yourself. So with that, let's talk about some of the myths that are out there. First myth is simply they're going to use the price as a gauge. Now, when you're looking at trying to reduce costs, increase profitability of the job, price is often cited as one area in which companies can reduce their costs, increase their margins, improve their profitability. We're going to challenge that a little bit. Okay? Second, cutting inventory costs can improve profitability. In some cases, that is true. You can do some inventory reductions. You can consolidate some of the cutting tools, how you're managing that within your own processes, and improve productivity and therefore profitability on the job itself. However, in a lot of cases, that doesn't work out so well. Next, there's a conception out there that, you know what? You don't need to talk to your CNC programmer before you start ordering tools. Okay, and we see this a lot. Requests come in, go into a purchasing agent goes through, they price out, something, and it may not be to spec. It may not be what the CNC programmers are looking for. They go with a cheaper tool, and hence they don't get the productivity or production out that they were expecting. So one of the things that we wanted to do when we talk about customers is let's take a look at the overall production cycle. When we talk to end users, we talk to our customer base, a lot of times they'll spend a lot of time in that first box, cutting tools. So when we're looking at trying to improve overall productivity, that's where they focus. In fact, some of them actually hyper-focus in that area, okay? But that's not where the real profitability is going to happen. The real profitability is down in that blue box called machining, okay? So we're going to try and talk to you about the difference between cost and production as it relates to cutting tools and cutting tool pricing, and how you can use that to help manage and gain additional profitability. So let's dive a little bit into tool cost. All right? Now, when we set about this exercise, there was a couple things that we wanted to do. We decided, you know what? We've had this on our kind of our punch list for a while. We wanted to take a cross section of tools, and we wanted to compare those tools against a standard toolpath, standard part, and run that through until we could kill the tool. You want to get some people like your application engineers, your CNC programmers excited. Tell them they can here's a bunch of tools, we want you to break them. You get a little excitement out of that one. And they certainly did. So what we went about was we selected 4 tools. We looked through catalogs, we looked through sources just like you guys do. And we picked out 4 tools across the board. And they ranged in prices, the exact same diameter, solid carbide. We tried to get similar quality as far as the cutting abilities. And we stuck to a specific ISO group. We want to focus in on, you know, your mid-grade steels, your tool steels, and so forth. And we wanted to make sure that we were dealing with a level playing field, okay? And then the third one, we were going to go with the cutting tool vendors' recommended parameters, okay? Now that's important to remember because the cutting tool vendors, they're going to specify what surface feed you're going to be running that particular tool at. They're going to specify what feed per tooth you're going to be using, and we went with it, okay? They're supposed to know their tools. We're going to run them. Okay, so the criteria. Here's our sample part. Now, this part was a piece of D2, okay? So you're looking at 31, 32 Rockwell. Not really hard, but challenging enough. The geometry in that specific part was designed for a specific reason. We wanted to make sure we got enough travel. We're going to be running a 3/8 inch tool through that material. We're going to go a 1/2 inch deep. Okay, so just a little bit over a 1/2 inch. So we're running about 1.5 times D. We're going to be running that 3/8 inch tool across, and we wanted to define enough geometry where it was challenging, where you had various types of motion that were involved. Tight areas, open areas, areas where you're actually going to be pinching in on the radius. So we wanted to come up with some geometry that, one, we could utilize a lot of travel, get as much out of it for tool life comparisons, and make it a little bit more challenging for the tool itself. So the criteria, if I can advance. All right, D2 steel, 3/8 inch, and we're going to use the same depth of cut, width of cut. Width of cut, we're going to use a radial chip thinning philosophy as far as defining what our speeds and feeds are. It's going to be a 15% step over, and when everything's all done, we're going to measure tool life, and we're going to measure material removal rates, because that's critical for defining what the real true production and the tool cost is involved. So, just out of curiosity, we have 4 tools. Here's the pricing. They're all within about 25 to 27% of each other, judging from the lowest cost tool up to the upper end. Okay? Any guesses which one wins? Okay. Save it. We'll get there. All right? Now, there's a few surprising things that happen. So, first off, this is the part that we decided to run, use as our benchmark. Again, there's a wide variety of geometry that are involved. The tools that we did purchase, just a couple comments. The high-end tool was capable of 2 times D. All the other tools, even though we're going through the same source, were 1.5 times D max. Okay, so we're trying to get the maximum amount of material removal out of each one of these. So the one tool, the more expensive one, had a little bit more leg room, had a little bit more runway to work with, and we basically ran through each tool, ran it to, you start seeing it's going to start glowing to the point at which we felt we were missing out on the tool edge, okay? We're actually compromising the tool to a point where, we can no longer get, useful life out of it. All right, so let's take a look at the numbers. 4 tools, each ranging from $112 down to about $88. All right, solid carbide. Okay, you have your tool price, you have material removal rate. Again, we're using manufacturer specifications for cut parameters. So you're going to see some variation here. On solid carbide tool 1, they were a little bit more aggressive with the cut parameters. However, The other three tool vendors had, they were a little bit more conservative with what they were running for feet per tooth and surface footage recommendations. All right, so the material removal rates really aren't there. Tool life, it ranges from 37 minutes all the way up to 63 minutes of solid in-cut time, cutting time. All right, everybody with me so far? All right, we're just going to assign some easy numbers. Let's put a machine burden rate of $100. We have our machining time, and we're going to look at 1,000 cubic inches. How much does it cost to use this tool to cut 1,000 cubic inches of material in D2? All right, so our machining time, you look at some numbers there, 413, 725, machine time in hours, okay, if we were to cut 1,000 cubic inches. And now let's take a look at costs, okay? The machining cost is pretty straightforward. That's your minutes times the amount of material, and now you get your hours, okay? Oops, there we go, all right. It's 689, 1,200, 2,500, and 25, 2,600, okay? So a wide range of cutting tool costs, okay? Just for the machining side of it. Now let's look at the tool cost, all right? Now what's interesting, if you look at tool life, you'll notice you've got some disparity up there, right? You've got tool A with 63 minutes. You got tool C with 218 minutes. That's some pretty significant tool life. If you are only weighing things against tool life, guess what will happen? If you look at tool cost, you got 737 against 665, okay? So what's happening here, all right? You have the classic hare against the turtle scenario, okay? The one tool that was running at 218 minutes, that thing would have cut all day long. But its cut parameters were set so slow that it could manage that. And it also had different geometries. Each one of these tools had different geometries. Helix angle, chip breakers, no chip breakers, okay? But they're all geared and focused on that one material group. So you're still looking at a P-ISO group, right? Now when you total everything up, so you have the disparity there, the more expensive tool was actually a lot more cost-effective than all the cheaper tools. So what's that tell you? Okay. They're almost in line, or they are in line, with the price. Okay? So the less expensive tool is actually costing you more to operate for 1,000 cubic inches than the more expensive one. Now, there are some differences, obviously. Price is going to come into play as far as manufacturability, the quality of carbide, the coatings that they're using, the manufacturing process, the design, the engineering behind the actual tool geometry itself. So there's a reason why you're paying extra. There's also a reason why you're probably getting through material a lot faster. Okay? So if you're trying to make a decision just based on price, it really just doesn't work out, right? So you can't really look at it when I said, you know, there's a difference between price and cost. The cost is really what you need to be looking at, the overall cost or the true cost. But wait a minute, okay? They're close in cost. Can we squeeze more out of it? Okay, now this is where it got really interesting. So we already knew what our benchmark was with the higher end or the more expensive tool. If we're running these other tools so slow, can we use the same approach? Let's just bump everything up. Let's see if we can squeeze out a lot more material removal rate, if we can drop down the actual overall cycle time to get through that material, okay? So, off to round two. Playing down a piece of D2, start all over. And what if we use the same parameters for all tools? So we're going to be running a tool that was typically somewhere in the 400 surface footage range all the way down to 300. Of those last 3 tools, we're going to be running that at 600 surface feet. Instead of 14, 16, and I think the other one was somewhere around 18 feed per tooth, we're going to bump that up to 2.5 thou per tooth on a 4-flute tool. And these are the less expensive ones, okay? So we're going to make it all even so that the material removal rate is going to be exactly the same across the board. All right? So now, let's apply the same parameters. And now you start to see something interesting. All right? So now, when you look at it, originally, your tool cut length was 1400 per se, 3700, 420, roughly, right? Okay? Now your tool life, 45, 218, 37. Okay, now we're going to be running these less expensive tools a hell of a lot harder and well over what they're normally spec'd out to. But when you look at it, okay, we've taken a hit on tool life, okay? We're down to 42 inches, 42 minutes, 37 minutes, and then 33 and a half. Okay, so that's pretty respectable. The cut time, the cut length itself has also dropped and increased depending upon the type of tool and which tool we were actually using. Okay, so again, there's some interesting data that we're getting back. Now, when we actually do the cost study, now let's take a look at the differences. So now, again, we're using the tool life. Our material removal rate is exactly the same. Okay, so we've overridden that. Our machining cost, exactly the same, because we've got the same material removal rate. But now our total tool cost is a little bit more in parity, right? So we've actually squeezed out considerable performance by actually bumping up the suggested cut parameters from the vendor. All right? Still, the dollars and cents when you get down to overall cost still doesn't equal the more expensive tool. Everybody see that? Okay? So we've gotten it down pretty close. And at this point, I think we've pretty much maxed out how high we can actually push the lesser expensive tools. We've maxed it out, everything possible. Now, looking at the numbers, you're probably asking yourself the same thing. Okay, we did the same thing. We asked ourselves a question. Okay, how can this be possible? We figured we'd get some improvement, but we also figured we'd break the tools a lot earlier. We also figured we'd wear them out and maybe not get the same cut length. The reason, and we should have known it up front, when we were running these toolpaths, we were actually using our own toolpath technology, dynamic motion. Well, there's an attribute to dynamic motion that kind of puts everything on a level playing field, and that's that dynamic motion actually gives you, let's see. Oh, before I get into that, let's go across the entire job. So now that we've had the cost related to 1,000 cubic inches, you're looking at 13. And if we start extrapolating that across, say you have a part, you've got 50 cubic inches of material to remove. The number of parts you want to run is going to be 250. Now you start moving that across the entire job. You've got 12.5 thou of cubic inches of material that you need to remove in this run. Now the difference between the lowest cost tool, even when it's been optimized, the lowest cost tool and the difference between the more expensive tool and the lower cost tool is now $10,000 on this one job. That's just tool cost. That doesn't factor into anything else related to tool changes, overhead costs, machine maintenance, everything. All right? This is just straight tool cost. So why did this happen? Why was the performance better? Again, we're using dynamic motion, and one of the things that dynamic motion actually does for you is it keeps a consistent chip everywhere on the part. So even if you're using an inexpensive tool, and we did this on purpose because We didn't want to be burying all the tools into corners. We didn't want over-engagement situations. So by using dynamic motion, ensuring that we're going to get a consistent chip across the entire part, we're putting everybody on a level playing field. However, that being said, that now points to us saying, you know what? I can take that inexpensive tool and I can bump up the surface speed that I'm using, and I can also bump up the feed per tooth. Now, looking at the specs, we ask ourselves, okay, so why are they speccing it out so low? Well, the reason being is most guys out there aren't using contemporary toolpaths, okay? Dynamic motion is just one of them that tries to keep a consistent chip throughout the entire machining process. There's others out there. But as a tool manufacturer, what are you guarding against? The last thing I want to see as a tool manufacturer is somebody breaking my tools, because now I've got a black mark on me, all right? So they're actually giving you specs for worst case scenarios. They're anticipating that you're going to be potentially running older style toolpaths. They're offset based. You're going to be burying that tool into a corner here and there. So they're going to back off their recommendations to make sure you're not going to kill their tool. And they want to try and maximize that tool life. Makes sense, right? Okay. So it's like, okay, it suddenly dawned on us, we could drive these things harder and get reasonable performance. Still doesn't live up to more expensive tools with the higher quality carbide, the better engineering behind it, but you know what? It's pretty respectable. So now, which tool wins? All right? We've already optimized the last three. We've pushed those as high as we can go. Again, the more expensive tool wins. It wins the game. But what about Mr. 112? Okay? When we started this, when we looked at the specifications for the tool at $112, that was their minimum recommendations. What if we were to bump that up? And we don't even have to bump it up a lot. What if we were to change the parameters on that? What does it look like if I bump up the surface footage, because I can, as long as I drop down my step over? If I drop down my step over, I need to increase some of the RPM, and which in turn is it's gonna get me into material a lot faster from an inch per minute range, right? If I bump that up, now what kind of effect does it have on tool cost? All right? So here, we bumped up number 112, we bumped it up to 750 in D2. We've gone, instead of a 15% step over, just to 10%. So we actually dropped what we're capable of, but because of that, we're now running, instead of 86, 85 inches per minute. It's not crazy, but we are up to 128 inches a minute. That's going to affect your material removal rate. So I've gone from roughly about 2.46 up to a 3.6 material removal rate. Okay? And that's pretty impressive. That's a significant percentage drop, jump. But now when you look at the overall tool cost, guess what? That tool cost has changed. It's dropped $400. So instead of being $1,500 where it was in its original settings, you're now looking at $1,000 to remove 1,000 cubic inches per minute. So you're looking at $1 per cube. And that's not too bad, okay? Especially for a 3/8 inch tool. All right, so what's the dirty little secret about tool cost? Well, it's not about price, it's about performance. And when we talk about performance, we're really talking about material removal rate as it relates to tool life. And you have to factor both of those into the equation. So if you're going out, you're purchasing tools, you really need to look at overall performance in order to gauge what's going to be best when it comes down to profitability on a job. All right? So it's not about, the numbers, I need 15 or 25 of these end mills, and yeah, I can get a deal on them, and I'm just going to order it out of a catalog and be done with it, and think I'm going to, be cutting my tool costs, so therefore my overall profits are going to increase, and the cost factors are going to come down. It doesn't work that way. Unless you're actually doing testing and you're paying attention to the technology that you're using to drive these tools, unless all three of those components come together, that's where you're going to start seeing big profitability gains. It's not just on the price, and you can't look at the price. I mean, we have customers all day long. Hey, we ask them, how come you're not using XYZ tool? Oh, we've looked at those. Those are way too expensive for us. We can't afford those. You can't afford not to use those. Okay? There's engineering built into there for a reason. They've already proved it out. There's value in that. So, again, it's not about price. It's really about performance. Okay? So, going back to our tool cost myths. Okay? If you're using price as a gauge, that's gone. Okay? It's no longer about just simply price. You have to factor in material removal rate and overall tool life, and even massage your cut parameters so that you're maximizing both as much as possible. And don't be afraid to play around with it. Yeah, you can cut some inventory costs, but you're better off spending more money in quality tooling and seeing your profits go up. Okay? That sounds like an oxymoron, but we have plenty of customers that are doing that. They're spending more money on tools and actually seeing their profits go up. Right? And lastly, you need to involve your CNC programmer. If you're making tooling purchases, you need to involve them in the equation, because they're the ones that are going to give you the benchmark data to actually justify what you're trying to purchase. Okay? They're also the front line, and those are the guys that are going to be talking to the tool vendors and getting their finger on the pulse of what's happening in the field when it comes to engineering, tool design, and some of the new methodologies, whether it's manufacturing or materials, that are actually going to be creating the production that you need. So the myths, they're gone. Right? So with that, I'd like to conclude. Does anybody have any questions? Yeah, question up there. What's that? Not necessarily. I mean, one of the next things that we're actually going to do is let's take a set of higher end tools and let's compare them. What are the differences? But until you actually test it out, you'll never know. Until you start comparing them and actually cutting real materials side by side, it's kind of hard to gauge. But the one thing we have seen, it's, there is value at that upper end of the cutting tool cost range. There is some definite value. Can you get and squeeze out performance out of the lesser expensive tools? Absolutely. You just still not going to match it up. Now, we were looking at, only 250 parts per run. What if you had 1,000, 2,000 parts you needed to run? 100,000. You start multiplying that out, and that's huge to your bottom line. Okay.
Hang on one second.
So, man, this thing is really loud. So what if you have really small part runs, like onesie twosies?
Okay, I was hoping that somebody was going to ask me that. If you think about it, okay, we're basically looking at 1,000 cubic inches of material, right? The math doesn't go away. It doesn't matter whether I'm cutting 250 parts or 5 parts. So if you have small volume runs, it still may be an advantage for you to be running, because if you purchase that tool, guess what? If you have any jobs that need that tool, you could pretty much guarantee that 1,000 cubic inches is going to produce that amount of money and only cost you that much. So now you can start projecting that over all your prototypes or all your short run parts. So it's, the math really doesn't change. So it works no matter whether you're looking at small runs or large volumes.
Any more questions? Who else? Come on. Who else?
Okay, one more.
Yeah, when you started, you said that tool cost was about 3 to 5% of the total production cost, and then you had in parentheses you had a 10 to 12.
Yeah, yeah.
What did you mean by that?
Yeah, for that, in most shops, you kind of, ballpark, and this is coming from industry, it's coming from even tool vendors. 3 to 5 is roughly the baseline. However, if you're in aerospace, you're a job shop that specializes in HRSA materials or difficult materials, you know what, that tool cost is going to go up. It's going to be between 8 to 12. It might even go up as high as 14 or 15%. So it really depends on the application.
Debunk that 3 to 5, right?
What's that?
The experiment didn't necessarily debunk the 3 to 5% standard. You didn't find anything different from the cost that you calculate.
No, not for that. Yeah, not for that. But if you're running exotic parts, guess what? That math still works. You're still going to save money over the long run. Okay.
Okay. There you go.
No, can you just go back to the slide?
Let's see. Like this one?
The macro scope of the machining and then all the breakdown.
Ah, okay, gotcha. Sorry, I'm going to have to step through it. And one more, right? That one there? Okay. All right. So when we talk about cost savings, I mean we can give away the tools, okay, at 3 to 5%, and it still won't have the same impact. If I'm able to go from $1,500 per 1,000 cubic inches of material volume, that's what I'm removing, down to $1,000, that's a lot more significant than that 3 to 5 cost. That's where you're starting to hit the machining, the productivity range. And what you're trying to do is you're trying to maximize your cam or toolpath performance along with the cutting tool capabilities. Now you start factoring in the machine capabilities on top of that, and can you start realizing 20, 25% productivity improvements? We have customers doing 30, 35% productivity improvements by marrying all those together and trying to optimize each as they relate to one another. So, yeah, tool cost, okay, yeah, it's on there. It's a cost center, but again, in a lot of cases, you can spend more money on higher quality tools and actually have a greater impact on job profitability. Okay.
Any other questions? Anything else? Other questions?
All right.
All right, well, let's hear it for Josh Mylek and MasterCam for sponsoring this afternoon's Brew and View. Thank you.
Okay. All right, thanks.